Hi, everybody, and welcome back. This is chapter 14, section 2 that we're continuing with, and it's going to be on the topic of airbursts and impacts. So far, we've talked a little bit about, some case studies of things that have struck the Earth, and then we talked about one of the theories and one of the predominant scientific theories on the formation of the Earth and why things tend to keep pelting the Earth. That is, things being particles, why particles tend to keep pelting the Earth, and that is from nebulas and cosmic dust. But now we're going to be talking about the actual objects themselves, these air bursts, that is, air bursts being objects that explode in the air, as the name suggests, and of course impacts being things that make their way all the way down to the Earth before making some sort of an impact or a crater. So some of the speeds vary quite a bit, but some of them can be as much as 45 miles per second or 72 kilometers per second. That's incredibly fast. Certainly much faster than the speed of sound. And so they enter our atmosphere, they create sonic booms, they create shock waves through the air, and even before touching the ground, they certainly make a major impact on the Earth. Maybe it's a bad choice of words. They make certainly they have an influence on the Earth even before touching the ground, even before impacting the ground. In many cases, they can be metallic or even, stony, as you would suggest, but even possibly metallic. If you happen to go to the Hall of Meteorites at the American Museum of Natural History, as some students have done, you'll find that touching meteorites, they actually feel very cold, almost like metal or like iron. In many cases, that is true. They are made of just that, rock and metal. As they fall through the atmosphere, they heat up due to friction. All right. Now, you see a shooting star because that's our nickname for these falling meteors. You see this bright light in the nighttime sky, and you think, oh, it must be really hot. And it is really hot because it's moving due to friction. But don't think of them as fireballs. Right? As these things hit the ground, once they stop moving and once the friction stops, they're actually very, very, very cold. Remember, these are stone or metal objects that have been in deep space, the cold, icy blackness of deep space for a long, long time. And even though friction, that is, them moving through the atmosphere, causes them to heat up and the outer layers melt off and glow bright light or bright color, once they stop moving, they go back to being very, very cold. It's very much like if you were to take I don't know, an ice cube, all right, and run it under hot water. All right, what would happen if you ran hot water over an ice cube? Well, the ice cube would melt off, all right, or part of the ice would melt off, and you'd have a smaller ice cube. But once you stopped moving that hot water over it, that ice cube would go back to being very, very cold. Think of it kind of the same way. So if you have a meteorite ever lands in your backyard and you touch it, you better have some gloves on, not because it's very hot, but because it's very, very cold. You could actually get almost frostbite by touching that. So anyway, a meteoroid. If you have not done the vocab for this yet, a meteoroid, OID, is anything that enters the Earth's atmosphere at these high rates of speed right here. So they can explode in the air in what we call an airburst, which the name kind of explains what that is. Tunguska in 1908 was a great example of an airburst. Exploded over the land and actually had much more of an impact because it was able to spread that energy over a much greater area, exploding higher up. Or if this meteoroid makes its way all the way down to Earth's surface, we call it a meteorite. So a meteoroid OID, has entered the Earth's atmosphere. Meteorite, ITE, is that same thing, but that has made it all the way down to the ground, and you can actually pick it up and look at it. Many of them are concentrated in Antarctica, and many of them are actually preserved in Antarctica because of the ice and the snow. But these meteorite craters are found, in fact, all over the world. So, as an object enters the atmosphere, we talked about the atmosphere several chapters back. Of course, it goes through the thermosphere, which is it's very thick in distance, but it's actually very thin in terms of density. So this meteoroid, this thing that is entering the atmosphere right there, is really just kind of plowing through very sparse atoms of air. oxygen and nitrogen and other stuff. All right, but as you get into the mesosphere and the stratosphere, where the air gets thicker and thicker and thicker and more dense, this vast moving object is plowing through more dense stuff, creating more friction, so it starts to light up, and it gets brighter and brighter. In many cases, air bursts, when it gets to troposphere, air bursts take place in the troposphere because the air gets so dense that it just can't travel any further without exploding. Chelyabinsk in 2013 was an airburst. Tunguska in 1908 was an airburst. So they didn't quite make it to the ground because the air gets thicker and thicker and thicker. If it makes it all the way to the ground right there, we call it a meteorite. All right, and it actually makes impact and creates some actual kind of crater. Okay, so these impact craters themselves, what do they do for us? What do they tell us? They tell us that something actually landed there at one time. It says something struck the earth, and it should be obvious. But wherever we see an impact crater, we can, first of all, search for pieces of the meteorite that hit the ground. And secondly, we can also kind of estimate how fast it was moving and what size it was. Barringer Crater, and this actually has a few different names. Barringer Crater in Arizona, also known as simply Meteor Crater, Meteor Crater, and that's actually the most common name for it. In many cases, these craters, these geological objects, are named after nearby towns, or actually nearby post offices in nearby towns. And then the nearest town, the post office, is the town of Meteor, so they call it Meteor Crater. Barringer Crater is the scientific name for it because scientists tend to name things after who discovered it, and a guy named Barringer was the first person to suggest that this was made by an impact. It also has the name of Canyon Diablo Crater, the Devil's Canyon Crater, and that's a nearby feature as well. But Meteor Crater is the more common one, and I'll show you this as well. This is very easy to see. It's out in the middle of the desert in Arizona. Chances are you've probably seen it already. All right. Well, this is a good example right here. Meteor Crater in Arizona. You have a rim that is raised up on the edge, and thrown out from the rim is ejecta. Now, ejecta, as the name might suggest, is stuff that has been ejected out of the crater, thrown out, and kind of thrown out in all directions, almost like spokes. All right, and some of these rocks that have been broken up are cemented together into a rock called breccia. Now, breccia is an igneous rock, and we think of most igneous rocks as being formed from magma or molten lava, which many of them are. But when you have these impacts strike the earth so quickly or so fast, it creates a lot of heat, and so you can actually have igneous rocks being made simply because of this impact right here. So rock chunks that were broken apart are fused back together, cemented together, to form a rock called breccia. And you know what? I'm sorry. I'm thinking of basalt. Breccia is not an igneous rock at all. I'll tell you what, it is made from heat. But breccia, I just lost my mind there for a second. Breccia is not igneous, it is sedimentary. Okay. We did not go through the rock cycle, but one of the rocks you may have studied, if you took earth science, was a sedimentary rock called conglomerate. What that is made of big pebbles, big round pebbles that are sort of cemented together. Breccia is the same type thing, rock chunks that are cemented together, but they're very angular instead of round. All right, so yeah, I misspoke. That is not igneous. That is sedimentary. Even so, these impacts, because of their high velocity and a lot of energy, create a lot of pressure and a lot of temperature. And so you can have rocks formed, even rocks that we know how they form on Earth, like igneous and sedimentary rocks, they can be formed simply because of this tremendous pressure and temperature. So breccia is a common one that we can find on Earth, but it's also made because of these impacts right here. All right, the kinetic energy. If you take physics, or if you took physics, you Anything moving has kinetic energy. It has the ability to do work. All right, so it creates a shock wave on the Earth and compresses a lot of the surface materials. In many cases, melts them. In many cases, even vaporizes them. So you have this giant crater on Earth's surface. The heat can also, and that pressure can also metamorphose rocks as well, and so melt rocks into other types. So all different kinds of rocks are formed because of these impacts. Okay, so right here is Meteor Crater in Arizona. Okay, and what you see is this upraised rim. You see how all the rest of the ground is somewhat flat around here, but as you get to the crater, the edges, it's really hard to see there, isn't it? Let's do red. The edges kind of slope up there and there, and it kind of slopes up all around. All right, that's part of what the impact does. All right, you also will notice that, I'll erase this stuff here, around the crater you see a lot of the stuff that looks kind of like rubble. Again, look at the surrounding landscape and see how relatively smooth it is. All the stuff, especially all over here. Actually, you see a little teeny tiny crater right there, but you see all around, immediately around the crater, this kind of buildup of rubble, all this rough stuff. That is ejecta. All right, that is stuff that was thrown up out of the crater. This right here, this piece was probably a pretty big chunk that got thrown out and made its own little mini crater after having been, tossed up out of the rim right there. And every now and then, sometimes erosion takes care of this, but you'll see things called rays. All right, what rays are these kind of spokes that go out sort of in all directions from a crater. Many of these you can see on the moon. The moon has rays, but if you have a great big arc of things being thrown out and it just kind of falls in a line right here on its way out, it makes this kind of ray of material. But anyway, that's Meteor Crater, of an impact crater. Well, here's another one I accidentally went to. We'll come back to this in just a second, but this is called Manicouagan Crater, or Lac Manicouagan. It means Manicouagan Lake in French, up in Quebec. So we'll get to that in just a little bit. But I wanted to show you some of the places in North America where we have impact craters, and it's probably more than you would think. The one that I just showed you is right here. That is Manicouagan Lake, or Lake Manicouagan. Did you know that an ancient crater was in an impact crater was right at the base of the Chesapeake Bay, right there. Arizona's meteor crater that we just looked at is right there, and there's others all around as well. I'm trying to think of any other ones that you would be familiar with. There is one I'll probably show you in class way up here in northern Quebec. But there's a lot of them, all right? And many of them have been worn down and almost unrecognizable because of erosion, but they're still there, and we can learn a lot from them. All right, well, there's kind of two different kinds of craters. We call them simple and complex craters, and the main difference is their size. Simple craters are generally kind of small, less than 6 kilometers in diameter. Now, that sounds pretty big, but some can be enormous, absolutely enormous. Barringer crater, or meteor crater as we're going to refer to it, is a simple crater. It just goes down and it's somewhat flat in the bottom and comes up. This would be a cross-section of meteor crater right here. By contrast, a complex impact crater is made, first of all, by a larger object, or an object traveling faster, so you can have a much larger diameter. You've got more of a collapse of the rim, and you've got an uplift of the center. Now, think about this for a second. If you have the ground right here, and here's your object flying down towards the ground, all right, what it's going to do, let's see if I can do this, all right, so this object is now plowing into the ground, getting all this, blowing all this stuff out of the way, okay, so this is ejecta right here. But the ground is compressing, all right, and so what happens is sometimes the ground rebounds after this, either after the meteor itself disintegrates or partially bounces out, or a little bit of both. What happens is this compressed ground, the bottom of the crater, let's see if I can do this. There we go. Rebounds back up, so that what you see is kind of like a central little point in the middle of the crater. There's a great example of one on the moon. In fact, let me see if I can get you a picture of that real quick. Here we go. This is a crater on the moon now called Tycho, Tycho. All right, named for an astronomer named Tycho Brahe. But anyway, you can see that there's this central uplifted point right here. You can see it in pretty good detail because of the shadows. All right, so what happens is the crater compresses and then the middle bounces back up. Very much like if you ever see like a drop of water drop into a surface of water, it compresses and then the water kind of bounces back up in the middle. That's sort of what happens right there with a more complex crater. So this is not on Earth, but this was certainly made the same way that a lot of these craters are on Earth. That is, by things impacting it. The difference is, the reason we have more of these on the moon, more craters on the moon, is because the moon has no atmosphere, and so it can't burn up things. So almost everything makes its way all the way down to the moon's surface and makes some sort of impact. Okay, remember how I said that the Chesapeake Bay had its own crater? All right, well, this is it right here. It's very difficult to see. You can't even see it from Google Earth, honestly, but it is still there. Many of these craters are detected by looking at sediments, sometimes even with X-rays, sediments underground. But so under the Chesapeake Bay, and so this right here, this thing that's sticking up would be that part of, I guess it's Maryland, but that peninsula that sticks down, the Delmarva Peninsula. Or I guess that would be Virginia right there. But anyway, that's that. And of course, this right here is the mainland over here. Well, this is the impact crater. And so underneath these sedimentary deposits, we have this very, very rough breccia. That what it was was sediment layers that were totally fractured into lots of angular, jagged little pieces and then fused back together because of heat. But it's certainly not as consolidated as all these nice smooth layers right here. It's all broken up in little teeny tiny pieces. But it does have a central peak, so that suggests that it was a complex crater. This is way down below in the lower sediments, but this crater can be detected, and we know that it's there. Here's the one I showed you before. Look how perfectly circular this is. That's pretty good symmetry right there. This is Manicouagan in Upper Quebec, and it's a complex impact crater. So the central part of this is raised up a little bit as well. This was actually I forget off the top of my head how many million years ago, but it was quite a long time ago, and so it has undergone some erosion by the elements. But that's another example of a complex impact crater. All right, so here's a list of some of the airbursts and impacts that have taken place on the Earth that are meaningful to us. Some of which are recent, some of which are pretty long time ago. Birth of the moon, well, we're not going to get into that, but according to some theories, the moon was a result of something striking the Earth kind of at an angle and then glancing off, but then getting stuck in Earth's gravity. Manicouagan crater, there we go, 214 million years ago. That's the one I just showed you. That's up in Quebec, in Canada. This one's important. I know you look at it and you think, how on earth do you pronounce that? Well, this right here is pronounced Chicxulub, all right? Or, no, I didn't even pronounce it right. Chicxulub, all right? I had to kind of practice that in the mirror once or twice. That X, it looks like Chicxulub or something. That X is kind of like an SH sound, all right? So it's Chicxulub crater, which once you hear it once or twice, it doesn't sound all that terrifying. This is in the Yucatan Peninsula, not far from modern-day Cancun, all right? This right here, this crater, is believed to have caused the extinction of a lot of the large dinosaurs. All right, this is another crater that is buried under many, many, many sediments, but had to be kind of detected through ways other than just looking at it. Let's see, I mentioned the Chesapeake Bay crater. Let's see, the Barringer crater, or meteor crater, that's what we're going to call it. That's in the United States. We mentioned Tunguska, that was in 1908, largest explosion probably to that point in the history of the world, as far as we know. And then 2013, Chelyabinsk, which is about the largest explosion since Tunguska. All right, so a lot of impacts and airbursts had taken place on our Earth, and many of which have been pretty significant. So like I said before, craters are much more common on the moon because the moon has no atmosphere. If you're standing on the surface of the moon, you're basically in space. You're just stuck to the moon, all right? Because there's no air, no gas of any kind to breathe. And so nothing will burn up these asteroids or meteorites, and so they all hit the moon and make some sort of a mark. By contrast, on Earth, since Earth's atmosphere does cause friction, a lot of these burn up, and so the atmosphere behaves sort of like a blanket or like a buffer that prevents our Earth from getting struck as often as the Moon does. The other thing that happens is as things do hit, especially on the Moon, more and more craters hit. You got more debris being flung up in the air. Well, I shouldn't say the air, just flung up. All right, and then it lands, and over time, older features are kind of eroded by being covered with dust by new impacts. So that does happen on Earth as well, but again, not as much as on the Moon because the Moon has no atmosphere to burn these things up. All right, and so you think of these impacts as being catastrophic events, which in their time definitely were. What it does, though, is it leads to a discussion about the rate at which things happen on Earth, or on any planet for that reason, or for that matter. But since we live on Earth, a discussion has come up. Has things happen on Earth because of big events all at once, or because of things happening gradually? And so we're going to talk about uniformitarianism, which we talked about ever since the beginning of the book. That is, the present is the key to the past. The rate at which things happen now is the rate at which they've always happened. All right. Gradualism, which is kind of a variant of that, and then there's catastrophism, which says that things happened kind of all at once in great big catastrophic, cataclysmic events. There was an archbishop in I want to say Scotland, I think. I can't remember now. Either Scotland or England. His name was Ussher, Archbishop Ussher. And he came up with the young Earth theory. And this was based on, again, being I think it was a Catholic or maybe it wasn't Catholic. We'll just say Catholic. Archbishop took the Bible and basically took the amounts of time mentioned in the Bible and said that that's how old the Earth was. All right, and so all the features on the Earth, he said, were a result of catastrophes. Things like objects striking the Earth, things like major, volcanoes and earthquakes and mega floods and tearing apart of the Earth in big events all at once, not gradually. And so that's how he said that the Earth could be possibly no older than 6,000 years old. Other people studying these landforms had a hard time accepting that they could be as young as 6,000 years old. But that's the theory, that the catastrophism is the theory that the Earth is young, and the way it got to the way that it is because of big events happening on the Earth. And I just remembered what Archbishop Ussher was. It wasn't Catholic. It was I want to say Anglican. He was Anglican. But anyway, it's a religious faith, and so that's where he got his information for the young Earth theory. By contrast, a man named James Hutton in 1785 introduced the idea of gradualism, which is kind of a form of uniformitarianism. That is saying that things happen at the same rate all throughout history. All right, and so as a result, since things move slowly, of course they didn't know about plate tectonics then, but if they could measure how fast plates move, they would say there's no way they could have moved this distance in 6,000 years, must be older. So he posited that the Earth must be much older than 6,000 years. And so the idea of gradualism or uniformitarianism came about by James Hutton. Okay, and like I said just a minute ago, plate tectonics is a great example of uniformitarianism. In the 20th century, how we were able to start actually measuring how fast plates move. That kind of supported uniformitarianism supported that theory, that if plates move very, very slowly, then over a certain period of time, you can figure out how long it must have taken them to move a certain distance. It certainly does account for certain catastrophic events like impact craters and rapid extinctions and volcanoes and earthquakes and earth-splitting types of events. And so what this did was eventually led to a theory called punctuated uniformitarianism. That is, if something's uniform, which, by the way, we'll go back to the definition of this word here. If something's uniform, it means it's all the same. All right? Uniforms, like sports uniforms, all look the same. Well, uniformitarianism means everything happens at the same rate. But punctuated uniformitarianism suggests that everything happens at the same rate, but every now and then you have big events that speed up the process. All right, mass extinctions, and you've got catastrophic events like impacts and airbursts and that kind of thing. So these are the various different theories as to how the Earth formed, and therefore how old it was. So I realize that was a lot. We're coming up on 25 minutes right now. I'm going to call that a section 2, and we'll pick up a section 3 in a different video. So in the meantime, thanks for following along, and I'll see you on the next one.